Hey, today we're going to introduce the concept of series and look in particular at a special type of series known as a geometric series. We start with any sequence a sub n as n goes from 1 to infinity. And recall that we came up with this concept of the nth partial sum of the sequence being simply the sum of the first n terms of the sequence. Well, we define the series, the sum n equals 1 to infinity of a sub n, as the limit as n goes to infinity of the nth partial sums. In other words, we create a sequence of nth partial sums, and the limit of that sequence is the definition of the series. And as usual, when we're talking about limits, if the limit exists, then we say that this series converges, and if the limit doesn't exist, then we say that it diverges. All right, this is a subtle point, this concept of a series being the limit of the sequence of nth partial sums. Hopefully we can make it clearer by looking at an example. Let's look at the series, the sum n equals 1 to infinity of 3 times 1/10 to the n. Our definition of a series started with for any sequence, and so here's the sequence we're talking about, the sequence of terms 3 times 1/10 to the n. And when n is 1, that's 3 times a tenth, or 3/10, or 0.3. And when n is 2, that's 3 times 1/100th, or 300ths, or 0.03, etc. So these are the terms of the sequence. And if we look at the first few partial sums, well, the first partial sum, the sum of the first 1 terms of the sequence, is just 0.3. And then the second partial sum is the sum of the first 2 terms. That's 0.3 plus 0.03, which is 0.33. And the third partial sum is 0.333, and you can see that the fourth partial sum is 0.3333, etc. So that the sequence of nth partial sums is the sequence 0.3, 0.33, 0.333, 0.3333, etc., and on and on and on forever. And it's clear that this sequence does have a limit, and the limit of this sequence is 1/3. And that's the key. That's how we define the series. The series is defined as the limit of the sequence of nth partial sums. So there's a sequence that is the terms of the series. That's this sequence right here. And from the sequence that gives you the terms of the series, you can compute the nth partial sums. And from those, you can make this new sequence, the sequence of nth partial sums. That's what we have right here. And then taking the limit of that sequence, the sequence of nth partial sums, that's what gives us the series. The series is defined, I'll say it yet again, because this is the subtle point behind series. The series is defined as the limit of the sequence of nth partial sums. And in this particular case, that limit is 1/3, and so this series converges to 1/3. Okay, let's look at another example, the series n equals 1 to infinity of -1 to the n. And if we look at the associated sequence of terms, the sequence of terms are -1, 1, -1, 1, -1, etc., and on forever. And from that sequence, we can compute the nth partial sums. The first partial sum is the sum of the first 1 terms, so that's just -1. The second partial sum is the sum of the first 2 terms, that's -1 plus 1, which is 0. And the third partial sum is the sum of the first 3 terms, which is -1. And similarly, the fourth partial sum is 0, because it's -1 plus 1 plus -1 plus 1. And so if we look at the sequence of nth partial sums, the sequence of nth partial sums is the sequence -1, 0, -1, 0, -1, 0, etc. And this sequence does not converge to anything. The limit as n goes to infinity of this sequence doesn't exist. The terms are oscillating between -1 and 0, not getting closer to any particular real number. And that tells us that the series, the sum n equals 1 to infinity of negative 1 to the n, diverges, because that series is defined as the limit of the sequence of nth partial sums. Okay, I want to talk particularly about geometric series, which are series where the sequence that you start with is a geometric sequence. Starting right in with an example, in our last video, we looked at the geometric sequence 10, 30, 90, 270, etc., which is 10 times 3 to the n minus 1 as n goes from 1 to infinity. And if we took a look at the corresponding geometric series, we could easily compute some of the partial sums. The first one is 10, the next one is 10 plus 30, which is 40, the next one is 130, etc. And if you look at the sequence of nth partial sums, it's really not hard to see what's going on here. They're growing larger and larger without bound. I think we found that S20 was some number of billions or trillions, I can't remember, but some very large number. And these are so going to, this limit is equal to infinity. The limit as n goes to infinity of the nth partial sums, infinity. And so this series, this geometric series, diverges because the limit of the nth partial sums doesn't exist. On the other hand, we just looked at this sequence, 0.3, 0.03, etc. This is also a geometric sequence. Each term is 1/10 the term before it. And so we can write this in our standard form as 0.3 times 1/10 to the n minus 1 as n goes from 1 to infinity. And we've already found that the associated geometric series converges to 1/3 because the sequence of nth partial sums of this original geometric sequence converges to 1/3. The limit as n goes to infinity of the nth partial sums is 1/3. And that's the definition of the series converging to 1/3. And so the point is that some geometric series diverge and some geometric series converge. And it would be really great if we could answer the question, which geometric series converge and diverge? And that's what we're about to do. We're going to determine under what conditions does a geometric series converge. And so we'll start with a general geometric sequence, a times r to the n minus 1, where r is the ratio of any term to the term before it. In other words, take any term, multiply it by r, and you get the next term. And in our last video, we very cleverly came up with a formula for the nth partial sum of any geometric sequence. And it's this formula right here. The nth partial sum is a times the quantity r to the n minus 1 all over r minus 1. We have that by the definition of any series, the series is equal to the limit as n goes to infinity of the sequence of nth partial sums. And since in this case we have a formula for the nth partial sums, we have that the geometric series, sum n equals 1 to infinity of a times r to the n minus 1, is equal to the limit as n goes to infinity of a times the quantity r to the n minus 1 all over r minus 1. So if we can compute that limit, that will tell us what the series is equal to. And the real question is, does this limit even exist? Or when does this limit exist? And the a is just a constant, so you can pull it outside the limit, and so it won't have any effect on whether or not the limit exists. Similarly, r is a constant, and 1 is a constant, and r minus 1 is a constant, and those are not really going to be the problem, except for the possibility that you can't divide by 0, so you have to be careful and make sure that r is not equal to 1. In other words, in the situation where r is equal to 1, the geometric series certainly does not converge because this limit does not exist. But aside from that concern, the thing that determines whether or not this limit exists is whether or not the limit as n goes to infinity of r to the n exists. And when does that happen? Well, if r is greater than 1, then the limit as n goes to infinity of r to the n is infinity. So that limit doesn't exist. And that was our example where we had r equals 3 for our series that was started 10, 30, 90, our sequence, our geometric sequence that started 10, 30, 90, etc. You know, what's the limit as n goes to infinity of 3 to the n? Well, infinity. It's even worse if r is less than -1. Imagine the limit as n goes to infinity of, for example, -3 to the n. Well, it's very similar to what happens to 3 to the n, except that the values that are getting larger and larger and larger are also oscillating back and forth between being positive and negative. So it doesn't just go to infinity, it simply doesn't exist. So in that case, where r is less than -1, then this limit still doesn't exist. We've also seen already that if r is -1 exactly, then the limit as n goes to infinity of -1 to the n doesn't exist. That sequence looks like -1, 1, -1, 1, -1, etc., and is not getting closer to any real number. And since we already know that r can't be equal to 1, there's only one possibility left. And that's the situation where r is strictly between -1 and 1, which is usually written as absolute value of r is less than 1. And in this case, the limit as n goes to infinity of r to the n is equal to 0. It exists and it's equal to 0. Just to see an example, suppose r is a half. If you're looking at the limit as n goes to infinity of 1/2 to the n, that's the limit as n goes to infinity of 1 over 2 to the n. Well, the numerator stays 1, and the denominator is getting larger without bound, and so that limit is equal to 0. And you get the same result for any r value that is strictly between -1 and 1. The limit as n goes to infinity of r to the n equal to 0. And let's make a little room. Oops, that's, I guess, good enough. We already have from above that the series sum n equals 1 to infinity of a times r to the n minus 1 is equal to a times the limit as n goes to infinity of r to the n minus 1 all over r minus 1. And if the absolute value of r is less than 1, then that limit of as n goes to infinity of r to the n is equal to 0. So you get this expression right here, which simplifies to a over 1 minus r. And what did we just do? We just said that a geometric series, sum n equals 1 to infinity of a times r to the n minus 1, converges to a over 1 minus r if the absolute value of r is less than 1. If that's not the case, if the absolute value of r is not less than 1, then we just said the series diverges. We have completely answered the question of when does a geometric series converge. It converges precisely when the absolute value of r is less than 1. And when it does, we even know what it converges to. We have a formula. It converges to a over 1 minus r. Just as an aside, this is very unusual. We're going to spend a lot of time looking at series and trying to determine whether or not they converge. Usually, all we are going to be able to say is, yes, it converges, or no, it does not converge. But we will very rarely be able to say what it converges to when we know that it converges. Geometric series, almost the only exception to that situation. The only time that we will be able to say not only that it converges, but what it converges to. Okay, let's do an example. Let's look at this geometric series, the sum n equals 1 to infinity of 1/2 to the n minus 1, which you can think of intuitively as 1 plus a half plus a quarter plus an eighth plus a 16th, etc., and on and on and on forever. In other words, the notation makes it look like it's an infinite sum. The only tricky thing there is you can't really add infinitely many numbers. And so we're not actually doing that. We're not taking an infinite sum. Intuitively, maybe we are, but precisely we're looking at the limit of the sequence of nth partial sums. That's precisely what's going on. And before we actually compute this one, let's remind ourselves of an alternate version of writing these geometric series, or we looked at it with sequences, but it's the same thing with series. We could look at the sum n equals 0 to infinity of 1/2 to the n. And it's exactly the same series, it's just a different way of writing it. In other words, when n equals 0, 1/2 to the 0 is 1. Just like when n equals 1, 1/2 to the 1 minus 1 is 1/2 to the 0, and that's where that first term of 1 came from. In any case, in our standard form, this is 1 times 1/2 to the n minus 1, meaning the a, which is always the first term, is 1. The r, the ratio between each term, is 1/2. Each term is 1/2 the term before it. And so our formula tells us that this series is equal to 1 over 1 minus 1/2. And 1 minus 1/2 is 1/2, and 1 divided by 1/2 is 2. And that tells us not only does this sequence converge, but it converges to 2. Which is actually not so hard to see in this case. Take this green line here and imagine that it has length 1. And if you start at the left and you move to the right by 1/2 a unit, you end up at this point here in the middle. And then if you go 1/4 of a unit more, you end up at this next point. And if you go 1/8 of a unit further, you end up here. And then if you add a 16th, you end up here. And if you add a 32nd, you end up there. And a 64th puts you in here. And you can see you can keep on doing that forever and ever and ever and ever. And what are you getting closer and closer and closer to? Well, a length of 1. And so that was starting with 1/2. And add 1 plus 1 and you get 2. And that's sort of the intuitive idea of why what this formula tells us really is correct, that this infinite series converges to 2. Okay, take a moment, see if you can find the sum of this series. Pause the video. When you're ready, start it back up. Writing it in its standard form, this is the sum n equals 1 to infinity of 1 times 1/3 to the n minus 1. And that lets you easily apply the formula. It's 1 over 1 minus 1/3, which after you simplify, you get 3/2. All right, try this one, only slightly trickier. Pause the video, and when you're ready, start it back up again. The first term is a 4. Each term is negative 1/3 times the term before it. And so the general form of this series is sum n equals 1 to infinity of 4 times negative 1/3 to the n minus 1. And then we're all set to apply the formula. You get 4 over 1 minus negative 1/3. 1 minus negative 1/3 is 1 plus 1/3. So this is 4 divided by 4/3, which is 4 times 3/4, or 3. Okay, that was our introduction to series, and in particular to geometric series. They are a little subtle. Try to keep in mind that the series is the limit of the sequence of nth partial sums. I know it's tricky, but that's what's going on there. It's just a limit of a sequence, a particular sequence. There's a homework on geometric series. Some of the problems are slightly tricky, but here's how you do them. They'll give you some nasty looking thing like sum n equals 5 to infinity of something or other like that you've never seen before. Write out the first few terms. In other words, if they write sum n equals 5 to infinity of something, then let n be 5 and figure out what the first term is, and then let n be 6 and figure out what the second term is. So write out the first few terms and then ignore what they wrote for the formula for the sum and rewrite it in the standard form. N equals 1 to infinity of a times r to the n minus 1, and then you'll be in perfect shape to apply the formula for the sum of a geometric series. Don't forget that the geometric series only converges when the absolute value of r is less than 1. If the absolute value of r is not less than 1, then it diverges and you're done. So, all right. There is, as you've probably gleaned, a homework. Have fun with it, and I'll see you soon.